Everyone, what we're going to take a look at today is, in fact, logistic regression. And as you can see from this name, it's a kind of regression just like a general regression, which is linear regression that you know. But the difference between these two is that the linear regression case, the y variable takes a continuous value, but in logistic regression, y takes discrete values. So it's a kind of classification technique and one of the most often used method for classification. And the classification is that, as I told you in the last class, is to assign an object into one of the predefined classes. And to make that classification model, we need a data set. So the model is a relationship between x and y, as you can see from this equation. We want to find this from a set of data, and that data consists of a set of records. So to find this model, the data set we use is called the training set. Okay, and in training set, each record, each observation, or each row has a set of variables, and among those, one is a class variable, target variable, that is denoted by y. Okay, so here L is a set of records, and each of these elements is the record, is an observation. So it has x values and y value. Okay, and x consists of p values. In the case of p independent variables, in the case of p x variables, and okay, and the other one is one class variable, which is y variable, and the y takes a discrete value. So just for the notation convenience, here we just use 1, 2, 3, and j. This is the in general form. This is the case of j classes. Okay, so here this index n means that we have n observations, n records, or n rows. So you can think of this kind of structure for a training set. There are n rows and p plus 1 columns, and among those p columns are x variables, and one column is for y variable. Okay, so this is an example of training set for breast cancer data, and as you can see from this figure, there are lots of rows here and bunch of numbers in this part. And here we have this one. Actually, this is a breast cancer data set. So this data set describes describes whether or not a cell is a malignant or benign. Okay, so this column takes only M and B. M for malignant, B for benign, and there are several x variables. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 columns, so 10 x variables. And those x variables are, in this example, radius, texture, so the radius of a cell and texture of a cell and perimeter, area, smoothness, compactness, and so on. Okay, so each of the columns indicates those properties for each of the cells, and those are measured by some mechanism for each of the cells. So in classification task, the training set has this kind of flat structure. Okay, so whenever we train a classification model, we use this kind of data sets. And from from that training set, we want to find a model for class variable y as a function of values of other variables, which is x. So we want to find this one, y equals to fx. Okay, just like linear regression. And the reason that we make this model, the reason that we find this kind of relationship between x and y is this one. The previously unseen observations should be assigned a class as accurately as possible. Okay, so the reason that we make this model is to predict the class of a new objects. So there's a new object x prime, and then we put that x prime into here, and then we predict its y value, its class. And so in this mechanism, a test set is used to determine the accuracy or goodness of the model. Usually the given data set is divided into training and test sets, with training set used to build the model and test set used to validate it. So once we find this kind of model, we should know about the goodness of this one, how accurate this model is. So what we do, actually, I will, in fact, I will explain about this in more detail later. But what we do in general is once we have a data set, for example, there are 100 rows, 100 observations, then we divide into two parts. The first one is used to train a model to find this relationship that is called training set. And we use the remaining set, which is test set, to see how this model is good. Okay, because both training set and test set has y columns, so it has the true values of y. So we can by using this set, we can see how good this model is. So just remember that once we have a data set, we divide the data set into two parts, training and test. And training used for finding this model, and test is to find, the test is used to validate this model. And here are examples of classification task. And in the previous class, I already talked about the application of classification using this second example, classifying credit card transactions as legitimate or fraudulent. So this is the case of the fraud detection case, whether or not each of the credit card transactions is legitimate or fraudulent. We want to predict that. Okay, and just like this case, I already talked about this breast cancer case. So we want to predict whether or not a tumor cell is going to be benign or malignant. We want to know that in medical example, in medical case. And sometimes we need to predict whether or not a news document or a document is going to be a finance or weather or entertainment or sports and so on. Well, actually, yes, whenever the document consists of a bunch of words, and based on that words, uh, they are transformed into variables, and then we can make a prediction model whether or not a new document is going to be the finance document or weather document or entertainment document. Sometimes we have to do that for classification. And the fourth example is the airline business case, and I'm not sure if you have this kind of experience, but I have. Actually, I booked a ticket as a economic seat because because the economy is cheap, right? And I was waiting for my flight at the gate, and then the staff at the gate called my name. I went to the front desk, and then they changed my ticket to the business class. But actually, usually the airline company, they sell more economic tickets than the number of economic seats they have, because of this no-show passenger who booked a ticket but did not show up for reason for the flight. So they sell, for example, usually if they have 100 economic seats, then they sell 120 tickets, because they expect that about 20 people would not appear to take the flight. Then they can make more money, right? But sometimes if their prediction uh, was failed, then it's possible that, for example, 110 people showed up, and then about 10 people should go upgraded, right? So I was that case. So what they want to do is they want to predict whether or not a customer is going to be a no-show passenger or a show passenger. If they can predict this rate exactly, then I think they can maximize their revenue, right? Their benefit revenue, right? Because they can sell more tickets and they don't have to upgrade some people. So whether or not a customer is going to be a no-show passenger or show passenger is a important problem to the airline company. And the last example, I also talked about this in the last class, and in manufacturing industry, it is also an important problem that we want to predict whether or not a product is going to be a defective or well-functioning product. Just to prevent that defective goes out to the customer. And for example, in battery manufacturing, this is a very important issue, right? Because if battery is defective, then for example, cell phone can be exploded. So it could be a kind of a dangerous situation. So based on the data set, process data set in the manufacturing side, they want to make a prediction model whether or not a product is going to be defective. So that is also another example for classification task. So the logistic regression is one of the most often used classification technique, and this is a kind of linear classifier, and you're gonna know why this is a linear classifier. And in logistic regression, what we're gonna do is look at three cases. The first one is binary logistic regression, and the second one is nominal logistic regression, and the third one is ordinal logistic regression. So as you can see from the name of binary logistic regression, this is the case where y variable, the y variable can take just two values. For example, 0, 1, positive, negative, good, bad, and so on, just like this. So y takes only two values. This is the case of binary logistic regression. But for nominal logistic regression and ordinal logistic regression, y can take more than two values. For example, in nominal case, y takes a or b or c. Y can take baseball, soccer, and tennis, something like this. And ordinal case, y takes more than two values, but in this case, there is a meaning of order. So it's like 1, 2, 3, or low, medium, high, something like this. So this is the case of ordinal, this is the case of nominal, and this is the case of binary. So in binary logistic regression, please remember that y can take only two values. And just for notation convenience in this class, we will use 1 and 0. Okay, and let us take a look at this figure. So because y can take either 0 or 1, and let us assume that there is only one x variable. So this x-axis is x, and this y-axis is y. Okay, and for example, in this example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 20 data points are there. And if we visualize it, this two-dimensional data set, we can make this kind of plot, right? And because y takes either 1 and 0, the data points are here and here, right? And if we fit a regular regression, general regression, which is linear regression, by least square method, then this kind of line will be found, right? This line. Because in least square method, we find this regression coefficient, which is intercept and slope, so that we minimize the difference between true value and predicted value, right? Then we're gonna find this kind of line. Then what is better about this line? If we use this regular regression, then the prediction for y can range from negative infinite to positive infinite, right? Even though the y value can take either only 0 or 1. So instead of this regular regression, in this case where we have just only two values for y, we use this kind of S-shaped curve. Then that S-shaped curve can be drawn by this formula. Okay, so here P is the probability that y becomes 1. Okay, P, probability that y becomes 1. And by this formula, we can draw a S-shaped curve, and this here the beta 1, I'm sorry, beta 0 and beta 1, beta 1, I'm sorry, I'll be back. By those two things, we can draw this kind of S-shaped curve, or this kind of S-shaped curve, this kind of S-shaped curve, and flat S-shaped curve by controlling these two things. If this one is positive, then we draw this increasing function. If beta 1 is negative, then we can make a decreasing function. Anyways, all of those are S-shaped curves. And what is good about using this formula, this S-shaped curve, to make a prediction model is that this P ranges from 0 to 1. Okay, so it can be think of a kind of probability that y becomes 1. And in fact, this formula is equivalent to this one. Okay, log of p over 1 minus p equals to beta 0 plus beta 1 times x. Actually, you can easily see that these two equations are equivalent by taking exponential on both sides. Then this left-hand side becomes p over 1 minus p, and this right-hand side becomes exponential of beta 0 plus beta 1 x. Okay, let me show you that. P over 1 minus p equals to exponential beta 0 plus beta 1 x. Then p equals to 1 minus p times exponential beta 0 plus beta 1 x, right? So rearrange this equation with respect to p. So just place p on the left hand side and then place the other things on the right hand side, and you're gonna get this formula. Okay, so these two are equivalent, and in this equality, in this equation, this part, log of p over 1 minus p is called log p. It's just kind of convention, kind of notation. So we call that, again, we call this part as log p, and by using this equation, we can see that this right-hand side is a linear form of x, right? Just like a regular regression. Anyways, in binary logistic regression, we use this formula for what? For making this kind of S-shaped curve. And based on the data set, just like a regular regression, we want to find this beta 0 and beta 1 from the data. We want to estimate those two things from the data. Okay, then how we can estimate those two things? Actually, we cannot, in this case, we cannot use the least square method, because actually we have y values, but we do not have this p value. So least square method does not work for this case. So what we do is we do maximum likelihood estimation. Here, the maximum likelihood estimation. The parameter estimates can be done by maximum likelihood estimation. So this maximum likelihood estimation is that MLE, you know, that I think you learned the concept of MLE from applied statistics 2. So what we can do from the training set, from the data set, so what we have is this one. We have set of records. In general, we have n rows and records, and it has x values and y values. Please notice that these y values are either 0 or 1. Then because y can take just either 1 or 0, we can say that y variable is a kind of random variable that follows Bernoulli distribution, where its parameter is pi. Pi is again the probability that y becomes 1, right? Then its probability mass function is given by this formula, right? If y is 1, then just put 1 at this position, then this goes out, and then just p remains, right? If this part is 0, then just put 0 here, and then here, then this part goes out, this part becomes 1, and only this part, 1 minus p, remains, right? So we can use this probability mass function for maximum likelihood estimation. So based on this data set, likelihood function is simply just, as you know, is simply multiplication of probability, multiplication of probability mass function for across all the data points from I to n for all those data sets. So here index I is the index for the data points, each of the data points. Then this likelihood function, which is multiplication of the probability, it becomes this thing, right? And then what does this mean? What does this formula means that if y value is 1, only this part remains. If y value is 0, only this part remains, right? So for the observation having y value of 1, we multiply the probability that y becomes 1. If the y value is 0, then we multiply the probability that y becomes 0. Okay? Then let's take a look at this simple example. In this example, there are 4 observations, 4 records, 4 rows, and among those, the first 2 observations having 1 on y value, y variable, and the last 2 observations having they have 0 values on y value, then the likelihood function becomes this one, multiplication of the probabilities, right? Then because the first observation is y is 1, we multiply p, okay? And because the second observation is the same, we multiply p, right? And third observation is y value is 0, so we multiply 1 minus p. And the last one is y value is 0, so we multiply 1 minus p. Because we use this formula, do you remember that? This formula, p equals to exponential beta 0 plus beta 1 x over 1 plus exponential beta 0 plus beta 1 x. You just simply plug that formula here, okay? Then the first term becomes this thing, the second term becomes this one, and third one becomes this one, and last one corresponds to the last one. And because the first observation has 10 for x variable, we just simply put 10 at this position, and 12 here, and 5, 23, right? So what we can see from this formula, all this formula, is that this likelihood function is a function of what? It's a function of beta 0 and beta 1. Okay? Those two are unknown variables. And we want to find those two things. We want to find beta 0 and beta 1 that maximizes likelihood function. And likelihood function is function of what? Beta 0 and beta 1, right? Once we plug in those values from the training set into that formula, then we're going to get this likelihood function, which is a function of beta 0 and beta 1, and we can find those two values by maximizing this, what is this one? This objective function in optimization perspective, right? But the thing is that, as you can see from this formula, this is a nonlinear optimization problem. But direct optimization of this likelihood function is kind of difficult problem. So instead of maximizing this function, we maximize log likelihood function, which is just log of this L function. Because the log function is an increasing function, maximizing this one is equivalent to maximize this thing. Okay? So by taking log on this right hand side, this exponent part goes down, this exponent part goes down and we take log here, then this first term becomes y times log p, and second part becomes 1 minus y times log 1 minus p, and this product becomes summation, right? And then this line is equal to the second line, right? It's just find the common part y and y log 1 minus p. Then by making this common part as a constant, a kind of constant, we can see that this part and this part becomes this one, right? And then only this part remains here. And for at this position, we just put this one. Then we're gonna get this formula. So actually, this part and this part and this line, they are all equivalent. And again, we want to find those two things, beta 0 and beta 1, that such that we maximize this log likelihood function. And please notice that this log likelihood function is still a function of beta 0 and beta 1, right? And because this yi is a number, is a value, this xi is a number value, and this one is number, right? So this log likelihood function is in three-dimensional space. This one is beta 0 and beta 1. This is log L. It's a kind of nonlinear surface. There must be a nonlinear surface, and then we have to find that I'm sorry, maximum point. Let us say that this z-axis is minus log L. Then we minimize this minus log L function. Then we have to find its minimal point by solving nonlinear optimization problem. So we have to employ optimization solvers such as gradient descent method or Newton's method. Actually, I'm not sure if you know those two things, and there are actually other nonlinear optimization solvers. Actually, we learn about those things in optimization class, such as Operations Research 2 or Operations Research 1. I will not talk about this thing in this logistic regression context, but I have to explain this thing, especially this thing will be explained in neural network contents. So without knowing this, actually we cannot understand the neural network. So at the time, I will explain about this one in more detail. But the thing is that please remember that this log likelihood function and is a nonlinear function of beta 0 and beta 1, and we have to employ this kind of nonlinear optimization solvers to estimate those two things, regression coefficients, beta 0 and beta 1. And again, then why this one is called maximum likelihood estimation? Because we maximize this likelihood function and we maximize this log likelihood function. And coming back to this part, we maximize this, right? And then what this means is that we want to maximize P for the observation having Y values. So for the observation having class 1, we want to maximize the probability that becomes that Y becomes 1. And for the data points having 0 for Y variable, we want to maximize the probability that Y becomes 0, right? So by multiplying all those probabilities, we want to maximize all those things simultaneously at the same time. Okay, that's the meaning of maximum likelihood estimation. Again, in summary, likelihood function is a multiplication of probabilities, and naturally we have to we have to maximize that multiplication of the probabilities. By doing that, we find those regression coefficients beta 0 and beta 1. So this slide shows the case of having only one x variable, right? There's only one x. But in the multiple independent variables case, in the case that we have several x variables, what we do is just we add the terms for x variables. So in the case of two x variables, what we use is this formula. Okay, so again, this is equivalent to p equals to exponential beta 0 plus beta 1 x1 plus beta 2 x2 over 1 plus exponential beta 0 plus beta 1 x1 plus beta 2 x2. Okay, so we can simply extend this scheme to multiple independent variables case. Okay, in general, px variables, we use this equation, this model. Beta 1 x1 plus dot 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 plus beta p xp. Okay, this formula is that. And from the data set, from the training set, once we find regression to these two regression coefficients, then for example we can have, so let us say that beta 0 is 5 plus beta 1 is 3 x, and 1 plus exponential 5 plus 3x. Then because the beta 1 is positive, we're gonna get this increasing S-shaped curve. And then once we have this thing, then for the new x, let us say that x is 7, then just put 7 this part, then we're gonna get the probability that y becomes 1 for this new observation. And if this computed probability value is greater than or equal to 0.5, then we predict the class for this new observation as class 1. If the computed probability is less than 0.5, then we predict this new observation as a class 0. That's the classification rule by using this formula. Equivalently, by using this formula. Okay, so the decision boundary, let us go back this example. So decision boundary is here, 0.5, means that on this x space, the decision boundary is here. If x is less than, let us say that this point is 55. If x is less than 55, we predict an observation. We classify an observation into class what? Class 1, right? Because the predicted probability, the computed probability is greater than 0.5. If the x variable is greater than 55, this area, we predict the data into class 0, right? Because the computed probability is less than 0.5. So the decision boundary is linear, right? The decision boundary is x equals to 55. It's a linear equation with respect to x, right? Is equivalent to x minus 55 is 0. It's a linear thing. And if you take a look at this case of having two x variables, then if there is a data points having 0 values on y variable here, and if there is a data points having 1 value on y variable here, then we're going to get this kind of S-shaped curve in three-dimensional space. And in this case, we still use the cutoff value of 0.5. So if the predicted value is less than 0.5, we predict as class 0. And if the predicted value is greater than 1, we predict as class 1. So if you take a look at to this direction from here to there, then that this decision boundary where the p equals to 0.5 is corresponding to this thing, right? So this part is class 0 and this part is class 1. Then here is a kind of S-shaped, S-shaped surface, and then the decision boundary becomes this thing, right? So it's a definitely linear decision boundary. Okay, so now you can see that the logistic regression is to find either S-shaped curve in the case of having only one x variable, and finding an S-shaped surface in the case of having more than one x variables, right? In the case of having three x variables, I don't know how that surface look like, because it must exist on four-dimensional space, and I cannot see that, but you can imagine this kind of figure. Okay, that is binary logistic regression. And here is an example, for binary logistic regression. Lead the problem in this example. A research is interested in how variables such as GRE, this is kind of English examination such as TOEIC, TOEFL, something like this, and we have to take this exam if we want to go to graduate school in the United States. And so this is a kind of English school. So such as GRE and GPA and prestige of the undergraduate institution effect, how those variables, those three variables affect admission into graduate school. The response variable takes either admit or don't admit, is a binary variable. So in this example, we have a historical information from some students. As you can see from here, this column is y variable. It takes either 0 or 1. So let us say that 1 is admit and 0 is don't admit. And this one is x1, x2, and x3, GRE, GPA, and rank. And we have how many? 400 data observations. 400. So this whole information from 400 students. And some of those are admitted, some of those are not admitted. They failed to be admitted. Okay, and their scores, GRE scores and GPA scores and rank, which is the to present the prestige of the undergraduate institution. So this one is rank, just first rank, third rank, fourth rank, and so on. So from this one, what we want to do is we want to find this model, rho p over 1 minus p equals to beta 0 plus beta 1 times what? GRE plus beta 2 times GPA plus beta 3 times rank. We want to find this model, which means that we want to find these 4 regression coefficients by maximum likelihood estimation. And because there are 400 observations and there are lots of numbers in there, so actually we cannot solve this likelihood function, this maximization problem of likelihood function by hand. So we have to use, for this simple example, actually, I think we can do that by hand if we know about the gradient descent method, but this case we cannot do that, so we have to use a software wisely. As I told you in this class, we will use a R software. So this is R code to find the logistic regression model, and because this is the first example, let me show you how to use R to find the regression coefficients. So so if you go to the iCampus, actually this is the screen that I can see as a instructor, and if we go to the data mining class iCampus website, then this part, the class material, then if you click this one, actually you can download those 3 data sets. Brand choice, this one will be used for the nominal case, and then this one I think will be used for ordinal case, and this one. So you can, this admission is the data set of this example. So you please download all those data sets, and then please practice this example and the other 2 examples by yourself. So download those 3 data sets, and I already have those things in my directory, which is data mining on the desktop. And so launch R software by please launch R Studio. Then R Studio, and what I usually do is I specify this working directory, and by clicking this thing, choose directory, and on the desktop, actually I have those 3 data sets here. Then I will open a new script. Then I will just copy these commands into my R script, and actually this symbol is just a prompt, so delete those things, and then this third line was supposed to be the second line, and this one I will delete this thing. So actually we have to read the data from outside the external file, which is admission.csv. So that data set looks like this thing. If you open this one using Excel, then the first column, it has only 2 values, 0 or 1, and GPA, GRE, GPA, and length, x1, x2, and x3, and this is y. So data set looks like this one, and there must be, yes, 400 records in this data set. Okay, so by running this command, read.csv command, we read a data set from external file, and because the first line, it has a column names header, this second argument is true, and I please hope you practice the R software, R commands by yourself, so that you can understand what each of the lines means. And because it's a CSV format, the separation is comma, and by learning this first line, you can see that we read a data set and it was stored as a R object which name is d.admin. So d.admin is this thing, right? Using head command d.admin. You can see several first few lines, and then the logistic regression can be done. Actually, the maximum likelihood estimation can be done. This GLM function, actually this GLM is short for generalized linear model, and the first input argument is this thing. So admit and tilde GRE plus GPA plus length. So this one is called a formula in R. So the spell of admit must be corresponding to this column name. So in formula, these four names must be same with these column names, okay? And then the second argument, we have to specify the data, the name of data, which is d.admit. And this part, it's just option. It's a kind of option to use this GLM function. And to perform logistic regression, what you have to do is you simply just specify this thing, binomial and logit. Then it performs binary logistic regression. So by learning this part, it's done. It's simply find the logistic regression coefficients, and by learning this part, summary function, you can see that the information for the fitted logistic regression model, which name is log R, and you can see that here this one intercept is beta 0, and this part the estimate for GRE is beta 1, beta 2, and beta 3. Okay, it was found by maximum likelihood estimation, and I will not explain about the remaining columns. It was about the significance of the regression coefficient. And in logistic regression, just for your information, in logistic regression, what we do is we do G-test. Unlike linear regression, in linear regression we do the t-test. I hope you please remember that. And in fact, actually, in this slide there is no information about this, but once we find this R object, once we have this prediction model, then we can make a prediction, right? Because we have those regression coefficients. By plugging in x values to this equation, we can find the probability that y becomes 1, right? Just put the GRE score and GPA score and length in this equation. Then this right hand side is just a constant. Then there's only one unknown variable, which is p. So we can find the value of p by using this equation, which means that we can predict the class of an observation. In R, how we can do that is to use this predict function. And the first input argument of this function is log R, the fitted logistic regression model in this line. Okay, then this is a model, and we have to specify the data to predict the class, right? So in this case, the data set, I'm sorry, the data set we have is d.admit. So just put d.admit, and then I will run this thing. I'm not sure how the output looks like. Okay, then those values are logit values. So specify as a certain argument type equals to response. Let me learn this part. Okay, then it shows the probability. Actually, just for your information, those values are logit values. On the computation of this part. Okay, logit value, logit, right? We say that this part is called logit. So these numbers are logit values. And if you specify this third argument, then it returns the probability that becomes y, that y becomes 1. Then I will store this result into y dot head. Okay. Then y dot head contains values ranging from 0 to 1, right? Then just simply using round function y dot head, you can see the predicted class. Okay, and actually I didn't plan this, but let me show you. Then let me show you one more thing. Then the true class is this one, d dot admit column of d dot admit. This one is the true value, true y value, right? This one is true. This one is predicted value. And then we can make a kind of a table which name is confusion matrix using table function. So this one is true value, and then predicted value is round of y dot head. Let me learn this line. Okay, let me learn again. Then you can see that 253 observations which y value is 0, they are correctly classified. But among the 0 classes, 20 observations, they are incorrectly classified as class 1. And among how many ones are there? 137 observations, and among those, only 29 observations, they are correctly classified, and these numbers are incorrectly classified. Actually, the true class was 1, but they are predicted as 0. So we can see that how this regression model is good by taking a look at this matrix. And again, this matrix is called confusion matrix. I will explain again about all those concepts later again. Okay, so coming back to this slide, using R software, we can find regression coefficients here, which means that we can find this model, this equation, and then we can predict the probability and we can predict the classes. Okay, that's everything about the binary logistic regression. So actually this shows several different link functions. In fact, this formula, which is equivalent to this one, here this log here, this whole thing is called link function, and actually we can use another formulas that are S-shaped curve or S-shaped surface, and this slide shows the examples of S-shaped curves. The first one is compete function. So you can use this formula. Okay, you can use log of minus log of 1 minus p as a function of linear combination of x variable. This one is also this function also can draw S-shaped curve. And as you know, the cumulative density function of normal distribution, so cumulative standard normal function, that function is also S-shaped curve. I'm not sure if you remember that the cumulative probability as x increases, it looks like an S-shaped curve. So instead of the logit function, this one, actually we learned this thing. We were taking a look at this one. So instead of this thing, you can use this format, and even you can use the inverse of cumulative standard normal function. And that's name is nomit function. And this case is called compete or converge function. And this case, the name is logit function. Okay, so the reason that I'm showing you this slide is that almost all commercial softwares, even including R software, even though R is not a commercial software, there are options what kind of link functions you want to use. So you can specify compete, or you can specify nomit, or you can specify link. So it's just kind of additional information then that I want to give you, so that you can notice that, okay, I can use compete function, I can use nomit function, I can use a logit function for binary logistic regression. So that's everything about binary logistic regression, and let's move on to nominal case. So I hope you please know the meaning of nominal. In nominal, response values are unordered, such as soccer, baseball, and basketball, A, B, and C, and what else? What else? Nationality, Korean, Japanese, Chinese, something like that. But there are still discrete values, just like this. Okay, in this case, we say nominal logistic regression, but still y takes discrete value, and the number of classes is greater than 2, right? 3, 4, 5, 6, 7, and so on. So in this case, what we have to do is, because we have, in general, let us say that in general we have capital J classes. So if this capital J is 4, then we have 4 classes, and if this one is 5, we have 5 classes. So in general, let us say that we have J classes, and even though I use the numbers 1, 2, J, because this is in the context of nominal case, please notice that this 1, 2, 3 to J, there's no meaning. There's no meaning in meaning of sequential orders. So they are unordered. It's just the reason that I'm using numbers here is just for convenience of notation, convenience of the equation using formula. So because we have J classes in this logistic regression, we should be able to find the probability that y becomes a class value J, small j. So if there are 3 classes, then we should be able to find the probability of this one, the probability of this thing, the probability of this one. Okay, we should be able to find the response probability. And the foundation in this context is that the sum of the probabilities must be 1. Okay, isn't it natural? Then just like binary logistic regression case, what we do is we use this logit model. Isn't it quite similar to this formula, right? And okay, I forgot to say that, I forgot to mention this, that this part p over 1 minus p is called odd ratio. Okay, so if those two values are the same, then odd ratio is 1, which means that this log value becomes 0. That corresponds to decision boundary. And if this value is, for example, 0.8, then this part is 0.2, then odd ratio becomes 4, which means that the probability that y becomes 1 is 4 times greater than the probability that y becomes 0, right? So this ratio of two probabilities is called odd ratio. So just like binary logistic regression case, in nominal logistic regression case, we use this model. Okay, so this is just for simplicity. Let us take a look at the case of having only one x variable. Then we use this thing, and here denominator part is p sub capital J, and numerator part is p sub small j, and here we have index j, and for the intercept we have index j. Let us say that, let us use alpha for intercept and beta for the coefficient of x variable. So we still use the same index here. So we use this one. So we use odd ratio of these two probabilities, and we take log, and we use this linear format of x variable. Okay, then I want to give you a question at this juncture. How many logits do we have to have in the case of J classes? How many logits? The answer is, because in front of me there is nobody, I cannot hear any answer. Classes, we should have j minus 1 logits, which means that j minus 1 equations. So for example, if we have 3 classes, we should have 2 equations of this form, 2 logits. In the case of 4 classes, we should have 3 logits, right? And this model is called baseline category logits, because we just pick up one class as a baseline, and we compare the probabilities with this thing to the other classes. So, for example, if we have class A, B, and C, right, 3 classes, then we should have P. Let us pick up B as a baseline. Then we should have this one, P sub A over P, because B is baseline, equals to alpha 1 plus beta 1 x, and log P sub C over P sub B equals to alpha 2 plus beta 2x, right? So in the case of 3 classes, we should estimate alpha 1, beta 1, alpha 2, beta 2 for regression coefficients from a training set. Okay, we should be able to find these 2 equations if we have 3 classes. alternatively, you can pick up C as a baseline, and for sure, you can pick up A as a baseline. Okay, then by setting up this thing, by setting up baseline category logits, actually we can derive the response probabilities from this equation and from this one. Let me show you that. So for the value of small j, for from 1 to j minus 1, so it means that we exclude the baseline class. Then for those classes, for these classes, the response probability p sub j becomes this one, and that is equal to this thing, and the baseline, the response probability for baseline class is this thing. Then by just plugging in this part here, we're gonna get this thing. Then why this probability is this thing? We can we can derive this one by using this property. The summation of the probabilities becomes 1. Let me show you that. Let me show how you find this thing. Then summation of j from j equals to 1 to capital J minus 1, summation of pj plus p capital J is 1, right? Then pj equals to 1 minus summation, am I right? I'm not sure. P of j. Then, okay, I'm right. Summation j minus 1, capital J minus 1 times p capital J exponential alpha j plus beta j x, right? So please use this part. Please rearrange this equation so that the left-hand side has p sub capital J, and then right-hand side has the remaining things. Then you're gonna get this one. Oh no, I'm sorry. You're gonna get this one. Okay, can you see that? So it means that from these two equations, it means that we can define response probabilities for all of the classes, which means that we can still use maximum likelihood estimation to estimate all of these regression coefficients. Okay? Find those regression coefficients, it means that we can compute response probabilities by plugging in new x value here. We can find those probabilities. For example, we can find P1, P2, P3, and then the classification rule is by taking a look at those probabilities. So in this case, is the number of classes is 3. By taking a look at those 3 probabilities, we assign to the class corresponding to the highest, the largest probability. So for example, if this value is 0.1 and this value is 0.3 and this value is 0.6, then we assign that observation into class 3, which corresponding to the largest value of the probability. Okay, that's this formula means that to explain the classification rule, just assign to the class having largest probability, simply. Then this maximum likelihood estimation, actually the concept is same as binary logistic regression, the maximum likelihood estimation of the binary logistic case. and I will explain about the meaning of maximum likelihood estimation for nominal logistic regression using baseline category logis in the next class. So I will finish at this moment, and then let's see you. I will see you again in the next sessions of the this week is a third week. Okay, I will explain about this one. I will continue on from this part. Okay, thank you for your attention. Bye.